This is the Chapter 8, Part 7 video on the Stereochemistry of Elimination reactions. So just as with the substitution reaction, the elimination mechanism matters in terms of stereochemical outcome. So what you can see here in this example is an E2 reaction, and you can see that with the E2, we're only getting one product here, the E as opposed to the Z alkene. Let's see what happens with the E1. In the E1 reaction, that same substrate, so this is the same substrate in both of these reactions, we're just using what we call E1 reaction conditions. You see the same major product, but we're also seeing a fair amount of this minor product over here. So this is not going to be a clean reaction like the E2. So the E2 is going to give you one product and one product only. The E1 is going to give you a mixture of E and Z isomers, and we'll talk a little bit later about why one is preferred over the other. So let's look a little bit more about what happens in the E1 reaction. So remember in the E1 reaction that the first step is the leaving group falling off. So once this happens, you get a carbocation intermediate, and the carbocation intermediate then at this point has freedom of rotation. So it can move around. You can see that this benzene ring here can either stay where it is when the nucleophile comes in, or it can rotate around in solution before the nucleophile attacks. So if it stays where it is and the base comes in, pulls off that hydrogen, we are ending up with the elimination product over here, right? And so you can see that happening. So this is the base coming in and pulling off that hydrogen. But if you get a rotation first, and that's what's being shown here on the bottom, so the molecule kind of rotates around a little bit, then the base comes in, pulls off the beta hydrogen, and electrons come down to form the alkene. So we have this product formed, right, that is different in terms of stereochemistry. So if we're looking at the outcome of the reaction, you'll notice that there is a preference for this product up here versus this product down here. And the reason why is due to steric strain. So if you'll notice, we had two big benzene rings, right? And those groups like to be farther apart, or far as apart as possible. So they actually prefer to be in this orientation. And you can see down here in the carbocation intermediate in the bottom situation that there's some steric strain between the two benzene rings. So this is less preferred and a less preferred alkene product, but it can still happen just because that carbocation intermediate has freedom of rotation and can move around. So keep in mind that in the E1 reaction, we are going to see some of both products. The bulkier your groups are, the more of the E isomer in this case. Though you do have to check and make sure, because just because the groups are bulky doesn't necessarily mean it's E, but the bulkier groups will be farthest apart versus in the minor product, the bulkier groups are on the same side, but this would not be preferred. If these are just kind of smaller groups, so let's say these were, fluorines, for example, we wouldn't see, as much of the major product here. You'd have more of the minor, and you might get something closer to a 50-50 mixture. The bigger these groups are, the more steric strain, and then the more of the major product you're going to see where the two bulky groups are farthest away from each other. Okay, now let's look at the E2 reaction. So the E2 reaction, we said before, had only one product as the outcome. The reason this is because the beta hydrogen and the leaving group have to be in this position where they are anti to each other, right? So they have to be perfectly parallel. If you were to kind of look down this side of the molecule here, would be what the Newman projection looks like, and you can see that the hydrogen, the beta hydrogen that you're pulling off with the base, and the leaving group down here, the X, they are perfectly anti to each other, or we can also use the term antiperiplanar to describe their orientation. So because of this, This is why we're only getting one product in the reaction. You absolutely have to have this orientation here for the reaction to proceed. Okay, so let's do a couple of examples. So here are situations with one beta hydrogen, meaning that there's only one hydrogen that you can pull off in the reaction. So for example, in this top situation, notice that what's happening here is the beta hydrogen is coming off. We have it set up so it's anti to the bromine. And when it does that, we're ending up with this E isomer over here. In the bottom situation, all that's changed is the position of the methyl group and the benzene ring. Okay, so they've changed positions. And now they're also going to change positions in the product, and we actually have the Z isomer. So it doesn't matter that one is sterically less hindered than the other, because there's only one beta hydrogen, so there's only one way for this E2 reaction to proceed. So in order to better understand this, we want to look at a Newman projection. So let's draw the Newman projection of this top molecule. So I'm going to draw the Newman projection looking down this angle here. Okay, so that means in the front carbon, the hydrogen is up. Okay, and then on the left here is going to be the methyl group. I'm just going to put Me here. And then on the right is our benzene ring, which I'm going to abbreviate PH. Okay, so now going to the back carbon. On the back carbon, notice the bromine is going to be straight down. On the top right is the H here. And the top left is the methyl group. So now you can see here the orientation between the beta hydrogen, right? That's our beta hydrogen. And our leaving group here. So our leaving group is down there, the bromine. And so the base will come here and pull off this beta hydrogen. The electrons are going to come down to form the double bond, and the bromine falls off. And you can see that what happens when this alkene is formed, that the two methyl groups here are going to be in the same side as the product. Right, those are the two methyl groups. And the benzene ring here is going to be on the same side as the hydrogen. So here's the benzene ring, and here's the hydrogen. So that's how we figure out the orientation. Let's look at this bottom one. So in the bottom one, the Newman projection is the same, except for we switch the orientation of the benzene ring and the methyl group here. So let's do that really quickly and see what that looks like. So on the front carbon, the methyl group and the benzene ring have exchanged places. Everything in the back carbon is the same. And now if we're looking at this, the beta hydrogen up here is going to be pulled off. Here's our leaving group down here. Notice that in this case, the methyl group and the benzene ring are on the same side, just as in the product. And the methyl group and the hydrogen are also on the same side, just as in the product. So that's how we can determine what the orientation of the product is in an E2 reaction where we have to worry about stereochemistry here. So you want to practice, notice that you want to practice drawing your Newman projections in order to get the correct product. Otherwise, it's hard to determine which one's going to be favored in this situation. So this is just kind of a quick recap where you can see here a substrate, and you can see here the base and the major product, and this is just going to show you how to do the Newman projection. So in this case, the Newman projection is going to be looking at, this is the front carbon right here. We're going to be looking down this way here. So this Newman projection is looking down this angle. So this benzene ring here is going to be on the left, and there's a hydrogen that's not drawn in that would be on the right when you're looking at this. The bromine would be straight down, shown in this position. And we go and we look at the back carbon, and notice the back carbon, the hydrogen is straight up. The benzene ring is on the right, and the methyl group is on the left. And here's our beta hydrogen straight up. The benzene ring is on the right, and the methyl group is on the left. So this is our anti-orientation. Notice that this is kind of showing you that you might not necessarily draw the first Newman projection correctly. So let's say you built a model and you drew this conformation over here. This one cannot undergo E2, this gauche conformation, because the beta hydrogen over here, which I've circled in red, is not anti to the bromine. And in this gauche conformation, the beta hydrogen is also not anti to the bromine. So what you might have to do is draw out all three Newman projections, find the one where the beta hydrogen and the leaving group are anti to each other, and this is the one that is going to lead to the product. And you can see that happening here, where we have this benzene ring on the same side as the methyl group. Okay, so this is what we have over here. Benzene ring on same side as methyl group, and hydrogen on same side as benzene ring. Hydrogen on same side as benzene ring. So that's how we're getting to the product there. Here's another picture so you can see what's happening. Here you can see the base coming in. This is what we call a kind of a sawhorse projection, but you could also draw the Newman projection of this if you like, if you prefer to do that. And so here comes the base, pulling off the hydrogen. The electrons come down, the bromine falls off, and now you can see the double bond is forming between these two carbons here, right? And so that's how we get the benzene ring and the hydrogen on the same side, benzene ring and hydrogen on same side, benzene ring and methyl group on same side, benzene ring and methyl group on same side. So either this kind of projection or the Newman projection that we went over on the previous slide would be effective for determining the stereochemical configuration of the product. In the situation where you have two beta hydrogens, this situation is a lot easier because we can choose which one is preferred. And you'll see that what ends up happening is very typically then you have a major product and a minor product. The major product, of course, is going to be the one that's less sterically hindered. So you can see that the two methyl groups are furthest apart. To understand this, you can also look at the Newman projections. So here's a situation where one beta hydrogen is being pulled off, right, versus the other. And you can see in these orientations how they lead to both the E and the Z products. So why is this E product the major product? If we were to draw the Newman projection of this, you would see that this is going to be the lowest energy Newman projection here. So this one is going to be quite favored. So I'm going to draw this Newman projection looking from the front here. The bromine will be down. The hydrogen will be on the right. And the methyl group will be on the left. On the back carbon, the hydrogen will be straight up. Our other hydrogen will be here on the left. And we'll have our methyl group down here. So you can see here that this is the favored conformation because the methyl groups are furthest apart. In the bottom orientation, we're going to have a gauche interaction. So the front carbon here is the same. And the back carbon is just going to be oriented a little bit differently here. Oops. So you can see here the Gauss interaction. So this interaction between the two methyl groups, that's a Gauss interaction. And that Gauss interaction is not going to be favored, right? So this Newman projection that we've drawn here is going to be higher energy, and so that is why the product here is going to be the minor product. This is the lowest energy Newman projection, and so this is going to be the favored product. Now, we don't necessarily have to draw out the Newman projections in this situation. If you kind of remember this situation when you have two beta hydrogens, that the least sterically hindered product is going to be the major product, that's fine. You don't have to draw out the Newman projection every time. In a situation where you have one beta hydrogen, though, you do have to draw out the Newman projection or the sawhorse conformation to figure it out every single time. Okay, so the last thing we're going to cover here in the stereochemistry of elimination reactions is chair conformations. So again, you can see that in the chair conformation, the hydrogen and the leaving group have to be antiperiplanar, and that actually means in a chair conformation that they must be axial. So let's look at what this means here. In this case, you can see that we have a chlorine in the axial position. So this conformation here will undergo E2. If this molecule does a ring flip and the chlorine or the leaving group here is in the equatorial position, you cannot undergo E2. So this top conformation is the only chair conformation that undergoes the E2 reaction. And so you can see here that it leads to product. So your base can come in. So this is going to be my base here. It's going to come in, pull off this hydrogen, electrons come down, chlorine comes off. Right? And so you have to have this particular orientation. Again, if there's not a beta hydrogen in the axial position, we can't do this elimination reaction. Or if the leaving group is not in the axial position, you can't do this reaction. In the case of the E1, however, since the leaving group falls off first, then either conformation can undergo elimination, right? So you have your heterolytic cleavage as your first step. You end up with a carbocation intermediate, and you can have then your base come in and pull off your beta hydrogen and form your cyclohexane product. So E1 reactions are going to undergo elimination regardless of the conformation of the starting material, whereas with E2 reactions, you absolutely must have that orientation where the hydrogen and the leaving group are anti to each other. So let's try a clicker question. Go ahead and give this question a try. So pause the video and see if you can figure out which of those products is going to be the elimination product when this starting material here undergoes an elimination reaction. And we're going to go ahead and assume that this is going to undergo an E2 elimination reaction. Okay, so hopefully you got the correct answer. Here the answer is A. One of the things that you want to keep in mind is how to number the groups here in this reaction. So let me go ahead and draw those in. So in this case, what I've done is I'm just going to go ahead and start over here at this methyl group. So what's interesting here is that you'll notice that at position 3, the methyl group here is in the anti-position, right? Or axial position, and the leaving group is also axial. So you can't have, there's no hydrogen at carbon 3 that can be pulled off, right? The only hydrogen that's there is equatorial. So that situation is going to eliminate answer C and answer D. That means the hydrogen that actually comes off is over here at carbon 5. And so this hydrogen here, I'm going to draw it in. That hydrogen is the one that's pulled off. So the double bond is going to end up being between carbons 4 and 5. At position 3, you have an up methyl group. So this is the up methyl group here at position 3. And at position 1, you have a down methyl group. So that's what's happening over here at position 1. That's why A is the correct answer. So what happens in a E2 reaction is that some of these can be very fast. And they are going to be fast if the preferred conformation, the preferred chair conformation, is also the one that undergoes E2. So that's what's happening in this situation. So there are 2 chair conformations of this cyclohexane. And this one over here is less stable because the methyl group and the isopropyl group here are in axial position. So you have the larger groups in the axial positions, and hence they're going to have 1,3 diaxial interactions, right, with hydrogens over here. So this is going to be less stable. The more stable conformation has the larger groups in the equatorial positions, and this is also the conformation that undergoes E2 because the chlorine is axial, and it also has a axial beta hydrogen. So in this situation, this substrate will undergo E2, so you're going to have a faster E2 reaction. You will have a slower E2 reaction when the preferred conformation, which is over here, does not undergo E2. So you notice that over here in this preferred conformation, all of these groups are equatorial, including the leaving group. So this molecule has to flip, do a ring flip, to get to this less stable conformer to then undergo an E2 reaction. So that process takes more energy, and it is slower because it's not already sitting in the conformation that undergoes E2. So this type of reaction is going to be much slower than the previous situation, right, where the more stable conformation already was set up to do the E2 reaction. So let's do a clicker question to give this a try. Go ahead and pause the video and see if you can do this clicker question. Okay, so hopefully you got answer A here. Answer A is indicating that this is a slower reaction, right? And that the product here is formed between these 2 alkenes. So let's quickly go over how we got to this answer. Okay, so I'm going to draw in the numbers here so you can see what's happening. So in order to solve this problem, we're going to have to draw out the chair conformation. I'm going to try to do it over here. We'll see how messy this gets. Okay, so I'm going to put my bromine here so we can see it pretty clearly. So this is carbon 2. On the left side of carbon 2, we have a methyl group going straight down. And then at carbon 3, we have a methyl group that's up. So it's going to be up and equatorial. And then at 4, we're going to have an up and axial carbon. So if we look at this bromine, we have to figure out where our beta hydrogens are. Okay, there's a methyl group blocking this axial beta position. So the hydrogen down here is the one that's going to be eliminated. And so this is carbon 3. So our double bond is going to form between carbons 2 and carbons 3. And that's what we see here, carbon 2 and carbon 3, carbon 2 and carbon 3. So we can eliminate B and D as options because the axial position has a methyl group, and so this is blocked. So we can't have a double bond form between positions 1 and 2. The other thing we have to consider is whether this is the lower energy conformation. And if you're looking at this, you'll notice that, oh hey, there's 1, 2 methyl groups here that are axial. We also have an axial bromine. We only have 1 equatorial group. And if we were to draw the ring flip of this, then we would notice that this would be the only group that would be axial. The other groups would go equatorial. So that means this is not the favored chair conformation. This is going to be the higher energy chair conformation. So it is going to be a slower reaction. The other chair conformation is going to be preferred. It's going to have to do a ring flip before it undergoes the E2 reaction. And that's what is going to make this a relatively slow reaction.